Now, this equation this system of equations that I've written right here, you know, all that stuff over there, that's really pretty easy after we see what's going on here. Instead of Q1 and Q2, I've used Y1 and Y2. So I've got Y1 and Y2 here, Y1 and Y2 here, in the same part of the equation where I used to have Q1 and Q2. And instead of Q1 prime and Q2 prime, I have Y1 prime and Y2 prime. So I'm generalizing the notation because not everything is a mixture problem. I mentioned you could have population model problems. Now there are all kinds of other problems that arise and give rise naturally to systems of differential equations, okay? In this case, systems of linear differential equations. And then we got a C1 and a C2. Remember, that's kind of where our R1A and R2B, our inflow rate from our source, came in. Okay, well, that's straightforward enough. Now we start putting this in the terms of linear algebra, and believe me, you've been warned. Everybody knows you've been warned that you are going to have to apply what you learned in linear algebra. And if you didn't learn stuff in linear algebra, you're going to have to hustle a little more. Fortunately, the stuff you need is not that extensive. What I'm going to do right here is something that I teach in pre-calculus and really should be taught in pre-calculus, and we certainly wish it was always taught in pre-calculus, but it isn't. Okay, so I'm saying that now we can express this as a matrix equation. We can express this as the column vector y1 prime, y2 prime is equal to some matrix times the y1, y2 column plus the C1, C2 column. You can see the C1, C2 there. You can see the y1 prime, y2 prime here. How the matrix articulates with the y1, y2 vector ought to be completely obvious to anybody who's refreshed themselves in linear algebra, assuming that your linear algebra gave you this information, okay? And in most cases, I believe it has. I know that the courses that people got from my colleague here certainly understand all this. I've had much experience with that over the years. Okay. So let's define this a little more clearly, though, and give a little more explanation to it. Your A matrix is A11, A12, A21, A22. And you can verify, you multiply the A matrix by Y1, Y2. It means you multiply this row by this column, and then you multiply this row by this column. And how do you multiply a row by a column? Okay, you got this row multiplied by this column. You take the first number in the row and multiply it by the first number in the column. Second number in the row, you multiply it by the second number in the column. I shouldn't have to be explaining this, but I really don't mind. I kind of love it. Okay. So what's that give you? It gives you A11, Y1. Well, what? Yeah. And it gives you A12, Y2. Okay, there it is, right? So that multiplying the first row by the column gives you something that goes in the first row, along with y1 prime, which is in the first row of this column vector, and c1, which is in the first row of this column vector. So that the first column has to read y1 prime equals a11 y1 plus a12 y2 plus c1. Well, then the same thing for the second column. A21 y1 right there. A22 y2 right there goes with the y1 prime and the c1 in the second row of everything, and that second row of all these matrices adds up to give you this. So that's how this matrix equation represents this. Now we get a little fancy with notation, and I define this big old capital Y with attitude, extra little line here, and an arrow over it. Well, here it is. Here it is with a prime, but let's talk about this one. We define this to just be our Y1, Y2. So, not sure, I pointed that out in class, but that's this thing, right? And our big old fancy C with attitude and arrow is this, a column vector. Y is a column vector. And Y prime, big old Y, fancy Y with an attitude, prime, is this. So that notation is really quite easy to understand and fairly obvious, okay? So that our matrix equation here is expressed even more compactly as this thing prime equals A times this thing plus this thing. In other words, A times our column vector of our y's, and if we go back to the mixture situation, that's just a column vector that consists of Q1 and Q2, right? But whatever y is within whatever model we're trying to work out, this is the A matrix times that column vector. This is the column vector of stuff over here that doesn't have a y1 or a y2 or q1 or a q2 on it. And this is the derivative of this column vector. And the derivative of the column vector is exactly what you expect. You just take the derivative of each of the functions. And of course we understand that y1 and y2 are functions of t. And as far as it goes, a1, your coefficients, a11, a12, and so forth, could be functions of t. We hope not, because we hope that they're constant, because it's pretty easy to deal with this if we have constant coefficients, and pretty darn difficult if we don't in most cases. Okay. Now, your book uses P instead of A for this matrix, and I use a fancy old P here, and a G instead of a C here, but otherwise the same notation. Their G is a little g, and they use boldface rather than arrows and fancy letters, okay? I wanted to make it real clear. So when you read your book, it's going to look like this. It's going to be lowercase g. The letters aren't going to be fancy, and but they're going to be bold-faced to indicate that they're vectors. Okay. Well, now let's just think for a minute. You don't have to have just two tanks. You don't have to have just two functions, y1 and y2. You can have as many tanks as you can build. Okay, and with modern technology, maybe we need to build robots to just keep building tanks and pipes and make these systems really, really big so nobody can understand how they work. But we can still write down the vector functions, or the differential equations, the interrelated system of differential equations that governs it, and even if we have constant rates and reasonable conditions, solve the darn thing, okay? And actually solve it rather easily if we have those kinds of restrictions. Okay, so, typically then, if you've got n tanks or n entities that you're interrelating with one another, wolves and mice and rabbits, and assuming you maybe have carnivorous mice or carnivorous rabbits or whatever, some kind of an ecosystem, whatever the system happens to be. You would write this system down as y1 prime equals, well, a linear combination of y1 through yn. And the convenient notation that's pretty universal for the coefficients, we'll call them a11, a12 through a1n for the y1 prime equation. And then we'll have some c1 over here, maybe a function of t, maybe not. Excuse me. And then for y2 prime, well, it's going to look just the same, except we'll use c2, of course, and we'll use a21, 2 up through 2n. And then down here to yn prime, we'll use an1, an2, ann, and cn. And that notation should be very familiar to you from linear algebra. It's really, I don't know an exception to the assertion it's universal, but I'm sure there is one. Okay, so right there we have it. Well, all I'm going to say is that this equation here, or this one if you prefer, represents this system just as well as it represents this system. I didn't specify how big these columns had to be. The y column here would have to contain n vector, n functions, and y1 through yn. So you'd have a longer column here. And of course you have n c's, and that's what makes up this thing, or this thing if you wish. And the derivative of this, well, obviously, the derivative of something that has n functions is going to have the derivatives of those n functions. It's going to have n functions. And your A matrix, naturally then, well, it has to be, every row has to have n entries so that you have something to multiply every one of the n functions in this column by. If you don't have compatible matrices. And since this thing has to have n functions, one corresponding to each one here, the derivative of each of these functions has to go here, this matrix has to have n rows because you need a different row to get everything that goes in here. And you really need to understand matrix multiplication so you understand exactly what I just said. If you don't, go back. Review matrix multiplication, review the dimension a matrix has to have to multiply a given vector to get a given type of vector and so forth. And then come back and listen to what I just said. Okay? So, in just considering this two-tank mixture problem, which is a fairly accessible question, you don't know how to solve it, but fairly accessible question, we get this model and we use this little very elementary linear algebra to write it in this form. And then we observe that we can extend it to any dimension and we have something that works. And we're going to develop solution techniques that'll work for any dimension, especially if your coefficients are all constant. Okay, now we want to talk about matrix functions a little bit, but it's pretty straightforward, and matrix functions behave just as you would expect them to. But we do need to talk about it a little bit.